Okay, continuing with chapter 21, section D, meh, I don't really think it's worth it, but I'll talk about it for a minute. Section E, we got some nice review coming at us, and section F, that is where the party is really at. So let's get going. Section D, look, if you want to memorize these rules, cool, go right ahead. I just don't really think it's worth it because when we get to section F, we're going to learn a technique that will help us integrate these functions just fine, and it'll also help us integrate other more complicated ones. So I don't really think it's worth your brain power to memorize these. I don't really think it's worth your time, but just for example, say you're integrating cosine of 5x plus 2, so the a value is 5, the b value is 2. This integral, according to the shortcut down here, is just going to be equal to 1/5 sine of 5x plus 2 all plus c. So like I said, you can memorize all 6 of these if you want to. They help you when it's not just x, when it's a linear function instead of just x. But like I said, we're going to learn a technique that'll handle more general examples than this, so don't worry about it. Section E, okay, so back in chapter 6, specifically 6E actually, we were studying rational functions, and we saw that we could take a rational function and rewrite it into a sum or difference of uh, two other rational functions by using a process called partial fraction decomposition. So if you need to, go back and check out the video for 6E to refresh your memory. Otherwise, let's move forward. So the idea here is that this integral, written as it currently is, it, it is impossible to integrate. There's no easy technique that I could teach you to help us integrate this one, except to rewrite the function itself using, obviously, partial fraction decomposition. So the denominator conveniently has two distinct linear factors, so we know that our original function is going to be equal to something over the first plus something over the second. We just need to figure out what the two somethings are. We multiply through by the overall denominator to rewrite it like this, and then we choose convenient values for x. So if we set x equal to 1, then this term is going to drop out, and we find out that b is equal to 2, and then we can set x equal to negative 1/2, and then we can work out what a is, and now we've got our decomposition complete. So when we take the integral, instead of taking the integral of the left-hand side, we're going to take the integral of the right-hand side. How do we do that, though? How am I going to integrate this piece or this piece here? Well, if you ignored my advice on the previous screen, then you may have already learned a shortcut to integrating functions of this type. If you followed my advice, then just wait until section F, which is coming up next, and then we'll know how to do this, but here's the answer anyway. Look, I'm just trying to go through the book in order here, folks. But I promise by the end of this video, you should understand how to evaluate that integral without too much difficulty. Okay, section F, this is what we're here for. We're now going to learn a technique called integration by substitution, or it's often referred to as U substitution because historically, for whatever reason, we use the letter U when we do this. We've got a formula from the textbook in the blue box. I have an alternative form that I prefer written down below. So substitution is kind of like the chain rule in reverse. Okay, you might have been thinking about the chain rule a minute ago when I was talking about having not just x in the function, right? Let's actually take a look at the rule down below. Let's take a look at this right-hand side and imagine what would happen if we wanted to differentiate this. Well, differentiating c, that's a constant, that's going to go. Here, now I have capital F of u of x. That's a composite function. So we need to use the chain rule. When I differentiate that, I'm going to get big F prime of u of x times u prime of x. But using the notation that we've seen already, big F prime is just the same thing as little f. So we can see now where the left-hand side comes from. This is big F prime evaluated at u of x multiplied by u prime of x. So how are we going to use this? Well, essentially, we're going to have an integral which is going to be fairly complicated, and we're going to try to rewrite it in such a way, or even just in looking at it, identify that there is uh, some function, the inside of which also has its derivative in the problem. Okay, so again, basically we're looking for a function, but also seeing its derivative within the integral. Let's take a look at some examples. Okay, we've got a lot going on here. Let's talk about this first one. So in looking at this, I notice that we have an inside function here. It's inside of a square root, x cubed plus 2x. And what is the derivative of x cubed plus 2x? 3x squared plus 2. So this is very convenient. This is set up very, very nicely for a substitution. So we look down here. We're going to take that inside function, x cubed plus 2x. We're going to set that equal to u. And then we're going to take the derivative of both sides of this equation with respect to x. On the left, the derivative of u with respect to x is just du dx. On the right, x cubed plus 2x becomes 3x squared plus 2. Back in our original function now, we're going to perform the substitution to rewrite it. So this inside part becomes a u, and then 3x squared plus 2 becomes du dx. Now remember that something like du dx, it's not really a fraction, but it can kind of behave like one, so we're just going to cancel the dx's. And now we've got this simple integral, u to the 1/2 du. We use the power rule, we get this answer, and then as a final step, we substitute back into x's. Taking a look at the second one, now this is where the book's methodology really frustrates me. So again, we're finding the inside function here. The inside function is going to be the exponent on the e, because the outside function is e to the power, and then the inside function is going to be the 1 minus x squared. Now when we look for its derivative, the derivative of 1 minus x squared is going to be negative 2x, which we don't have inside of our integral. We have a single x, and that's good because that's close enough. We can work with that. Now what the book does is they kind of skip a couple steps here, and in the next line they just throw a negative 1/2 out here and then a negative 2 inside, because they're planning ahead and they know they want the negative 2x from the derivative of that. So now they've made that, and of course negative 1/2 times negative 2, those are going to cancel out, right? So they're setting themselves up for the substitution before they even show you what it is, which, okay, we got it over here. So, so the book's methodology is to figure out what du dx is, recognize that's negative 2x, and then try to create it within the integral. So you throw in the negative 2, and then you throw in something to cancel out with it on the outside. And from there, it's easy enough. Again, our dx's are going to cancel, leaving us with just the integral of e to the u du. That's simple enough. So that gives us negative 1/2 e to the u plus c, and then again, final step, change back into x's for your final answer. Now, if it's me, I would organize my work a little bit differently for both of these. You can see my process starts off the same way as the book's examples. I figure out what my u is, and then I take the derivative on both sides with respect to x. Now, whereas the book wants us to take the 3x squared and perform the substitution directly on that, I think it's better to actually do one more step of algebra, separate the du and the dx now, and get the du alone, because then when we look back at the equation, we see, hey, I have 3x squared plus 2 times, if you will imagine that the dx is a number or something that can be multiplied by. It's 3x squared plus 2 times dx, and I do have that right here, so I replace that with the du. And then I get to the exact same place as the book did. I have integral square root of u for in there, and then this whole thing becomes a du, and again, that's an easy integral to work out. For me, this technique is especially helpful in examples like the second one. So again, I start off the same way, u equals 1 minus x squared, take the derivative with respect to x, du dx equals negative 2x. Now, I get du alone. Du is equal to negative 2x dx. Now I look back at the original, I don't have negative 2x dx, I have x dx. So I want to make this into x dx, and I do that by simply dividing both sides of this equation by negative 2. And now my x dx becomes a negative 1/2 du. And I put that back into my integral, so I have the integral of e to the u, and then my x dx becomes a negative 1/2 du. The negative 1/2 can come outside of the integral, and then I just have integral of e to the u du, which is very easy, and we proceed exactly as the book did on the previous screen. So I really recommend doing it that way, but if you like the book's method, that's fine. For the remainder of the examples, I'm just going to be showing you what the book's work is. We can work through it. I really don't like A, the methodology, and B, the layout. Like I really hate how they're transforming the equation before even showing you what the substitution is. It doesn't make any sense to me. But anyway, let's look at some more examples. On the left, integral of cosine cubed times sine. Again, we want to try to find an inside function, which in this case is going to be the cosine, because that's cosine cubed. Cube is on the outside. If we choose that as u, then our du becomes negative sine of x. We perform our substitution. We end up with this integral here, which is very easy. Power rule, substitute back into x's. Sines and cosines can be a little tricky because you may immediately latch on to the sine and say, oh, well, the derivative of sine is cosine, so I should set u equal to sine. Well, no, not really. Again, you really want to try to find an inside function when you're doing this. Or, in the next example, you want to choose a denominator. And I'll talk to you in a minute about what your strategy should be for choosing your u. But in this case, we actually do want the u to be the sine. So we're going to set u equal to sine of x, and du is equal to cosine of x. And then, again, in my notation, cosine of x dx, that's exactly what we have right here. That just becomes a du. And so we have 1 over u du. That's a pretty easy integral. We should recognize 1 over x as the derivative of ln of x. So this is going to give us ln of, again, absolute value of u plus c, and then change back into x's. And then a helpful tip from our friend. Anytime, and this I will repeat this many times, I'm sure. Anytime that we see an integral which is initially of this form, where we have a function in the denominator and its derivative in the numerator, as soon as you see that structure, you can kind of skip over all these substitution steps. Just the answer is going to be the ln of the absolute value of that denominator's function. Because remember what happens when we take the derivative of an ln. When we have any inside function, it doesn't matter what it is. We differentiate it. That gets us 1 over f of x. But then chain rule, we need to multiply by the derivative. So we have the derivative over the original function. So be on the lookout for that. This comes up fairly often. Anytime we have an integral of the form derivative over original function, that integral is equal to ln of the absolute value of the function, plus c, of course. Since I just mentioned it, I've been talking about it a little bit, when we're choosing our u, we want to always first look for an inside function of some kind. That's something that's either inside of a square root, or inside of parentheses that has an exponent, or something like that. And we also want to look for denominators of fractions. Really, you could even think of that as an inside function where it's just something raised to the -1, right? Because that would put it into the denominator. If we've got a fraction where the denominator has something raised to a power, then you probably want that inside piece down there to be u. This is where I would always start when I'm dealing with substitution. Right? Look for an inside or a denominator or something that's inside in the denominator. The next couple of examples are just going to use that idea. After that, we're going to look at some special cases. They're on screen now, so I'll just mention them. If your function happens to have something like this, where a is a constant, so square root of whatever, say this was 9 minus x squared, then our a value would be 3 in that case. The substitution you want to use, this is a little different, they actually want you to change x into a, so whatever number that was, times sine of theta. So if that were, again, 9 minus x squared, then the substitution we would use is going to be x is equal to 3 sine theta. And then you would differentiate both sides with respect to theta. So you'd get dx d theta equals, in this case, 3 cosine theta. And you'd work the substitution from there. We have a special one here using tangent and another one using secant. Now, in the past, the IB has always said, like, hey, using the substitution, x equals a secant theta or whatever, solve this integral. So they've always told the candidates how to do those problems. I don't know if they always will, but as far as I know, they always have. So that's good. That being said, I do encourage you to try to commit these to memory if you can. So now let's look at just a few more examples of kind of the normal kind, and then we'll see these weird ones. So here we have sine cubed. So our inside function in this case is obviously sine, although we don't have a cosine anyplace. But perhaps we can make one occur. So we've got this power of 3 that we can play around with. Sine cubed is, of course, equal to sine to the first times sine squared. And from there, we can now perform a substitution on the sine squared because we know that's equal to 1 minus cosine squared. Now we need to choose our u. Now we need to be smart here. If we set u equal to sine of x, well, then the derivative is going to be cosine of x, which we don't really have. We have a cosine squared. That's difficult to work with. It's okay if we have cosine multiplied by a constant, as we saw in a previous example, but squaring it, that's no good. If we set u equal to 1 minus cosine squared, then our du is going to be negative 2 cosine of x multiplied by negative sine of x, which is very complicated and absolutely not what we have here. So we actually have to think a little more creatively in this case. And the answer is going to be just to set u equal to cosine. And that ends up working out pretty nicely because we can put that in for our u and have 1 minus u squared. But then our du is just negative sine, which makes this equal to negative du. You could either put a negative out in front of your integral, or as they've done, just switch the order of your subtraction. And now this is an easy integral to work out. Again, we use the power rule and then substitute back into x's. So sometimes we need to be kind of creative with our use of substitution. It's not always as easy as just choosing an inside or a denominator. There are a bunch of formulas called power reduction formulas for trig integrals. These are not required to know for the IB, nor are they required for the AP as far as I know. Again, you can memorize these if you really want to, but I wouldn't expect the IB to throw anything bigger than sine cubed at you, and I think you're smart enough to figure out to change that into, you know, sine to the first times sine to the second. But we can see that this first example here would have worked for the example that we just worked out. If we set n equal to 3, it does all work out after a few steps without having to use the process that I showed on the previous screen. So these do work if you want to memorize them. I certainly have absolutely none of these memorized. Never have in my life. Never will. Okay, back to some more normal stuff. This function has a pretty obvious inside piece, and that's 5x plus 1. So that is what we're going to set our u equal to in this case. So du dx is equal to 5. Dx is therefore equal to du divided by 5. Here's where I run into a problem. I don't have a dx, I have an x dx. right? Now, I could multiply both sides here by x, I suppose. I could give myself x dx equals x du over 5. But that doesn't get me anywhere. If I substitute the x dx for x du over 5, I still have the same problem, which is that I'm going to have two different variables in the integral. I'm going to have an x and a u. This is no good. So sometimes we're going to have an additional step that we need to go through in order to address this, which is just to look here at your original substitution and recognize, oh, you know what? If I can write u in terms of x, that means I can write x in terms of u, because x is going to be equal to u minus 1 all divided by 5. And then from here, the integral again becomes pretty easy. I'm going to factor out this 5, just give myself 1/25 out front, and then multiply u minus 1 by the square root of u, and that just gives me power rule. That's easy to do. Power rule, substitute back into x's, multiply through by the 1/25, and we're good. Notice that when I distributed the 1/25 multiplied by c, I didn't write this as c divided by 25. I'm just leaving it as c, because a constant divided by 25 is still a constant. This kind of double substitution technique where you end up with two variables after your substitution and you need to substitute a second time for the x, that's pretty common, so I definitely want you to be comfortable with the ideas in this example. Now, let's look at some of those weird ones that I talked to you about before. So again, the IB, if they were to give you this integral, they would also tell you, use the substitution x equals 3 secant theta to evaluate this integral. Using that, it's pretty clear that our integral is going to become square root of 9 secant squared theta minus 9 divided by 3 secant theta. But then we also need to change the dx. So that's where our derivative here comes into play. Dx is going to be equal to 3 secant theta tangent theta d theta if we multiply that over. So that's why we've got this term here. And then we're just going to do a little bit of algebra to clean this up. I've got a secant in the denominator, secant in the numerator. Actually, I got 3 in both of those, so that's cool. Here we've got a 9 and a 9, so we factor out that 9, take the square root of it, that gives us a 3 outside. Square root of secant squared minus 1 times tangent. But secant squared minus 1 is equal to tangent squared. And then we take the square root of tangent squared and we get tangent. And then tangent times tangent is tangent squared. And then we use trig substitution again, because tangent squared is, as we just established up here, secant squared minus 1. So 3 times secant squared minus 1 gives us 3 secant squared minus 3. And then finally, we can integrate this. The integral of secant squared is tangent. That's just a constant. So we've got an answer in terms of theta. Got to know your trig substitutions in order to get through a problem like this, guys. But now we need to substitute back into x's. Well, I know that x is equal to 3 secant theta, but that doesn't really help me with the tangent of theta or just the ordinary theta here. So here's how we're going to address that. From the original substitution, if we solve for theta, well, first of all, x over 3 is equal to secant. Probably easier to think about things in terms of cosine, so we take the reciprocal of both sides. And then clearly then theta is just going to be equal to the arc cosine of 3 over x. So now I know what I'm going to put in for there, arc cosine of 3 over x. What about tangent of theta? Well, I know what cosine of theta is. I need to work out what tangent of theta is. There's two ways to do this. One way is illustrated here using the right triangle. Since we know that the cosine of theta is equal to 3 over x, if we draw a right triangle with an angle theta, the adjacent side has to be 3 and the hypotenuse has to be x, since its cosine is 3 over x. And then we use the Pythagorean theorem to work out what the opposite side has to be. In this case, square root x squared minus 9. Now, using this right triangle, we can work out that the tangent of this angle is opposite over adjacent. So we just put that in for that, and then we have a nice final answer. The other way that you could have worked out what tangent is you could use your Pythagorean identity that cosine squared plus sine squared is equal to 1. You know what cosine is, therefore you know what cosine squared is. Therefore you could work out what sine squared and then sine is, and then you could use tangent is equal to sine divided by cosine. I don't know, I like the right triangle method myself, but as always, you have options. We'll end this video right there. There's a lot to practice here. You absolutely need to be comfortable with substitution. Not learning the substitution method would be like not learning how to use the chain rule with derivatives. You're only going to be able to do very basic problems without it. So absolutely, you got to spend time with this topic and just practice a lot of different examples, and eventually you will feel comfortable with it. As I said in the last video, I really recommend integral-calculator.com. Put in the integral that you're having trouble with. It'll show you the answer. And then if you wanted to, it'll show you the steps. It's free. It's awesome. It's really, really helpful when you're first learning this stuff.